Chapter 5, Electromagnetic Induction. Okay, electromagnetic induction is actually the production of an induced EMF in a conductor or coil whenever the magnetic flux through the conductor or coil changes. First of all, we are going to learn about magnetic flux. Okay, so at the end of this chapter, students should be able to define and use magnetic flux, which is we know that flux equal to B dot A or BA cos theta. And for the second part, okay, students should be able to use Faraday's experiment to explain induced EMF. Magnetic flux. Let's discuss about the phenomenon of electromagnetic induction. From the experiment, when the bar magnet is stationary, the galvanometer not show any deflection, meaning that no current flows in the coil. When the bar magnet is moved relatively towards the coil, the galvanometer shows a momentary deflection to the right. When the bar magnet is moved relatively away from the coil, the galvanometer is seen to deflect in the opposite direction. Therefore, when there is any relative motion between the coil and the bar magnet, the current known as induced current will flow momentarily through the galvanometer. This current due to an induced EMF across the coil. So, as the conclusion, when the magnetic field line through a coil changes, thus the induced EMF will exist across the coil. And the magnitude of the induced EMF depends on the speed of the relative motion, where if the V increases, induced EMF increases, and when the V is decreases, induced EMF also decreases. So we can conclude that V is proportional to the induced EMF. Magnetic flux of a uniform magnetic field. So what is meant by magnetic flux? Magnetic flux is a scalar product between the magnetic flux density B with the vector of area A, or mathematically phi equal to B dot A, and since dot product, the equation is also BA cos theta, where phi is a magnetic flux, theta is angle between direction of B and A, B is the magnitude of magnetic flux density, and A is area of the coil. Magnetic flux is a scalar quantity and the unit is Weber or Tesla meter square. Okay, consider we have a uniform magnetic field B which is passing through a surface area A of a single turn as shown in the figure. So from this figure, we should know that the theta is actually equal to 0 since the vector of area should be perpendicular to the surface of area. Therefore, the B and the vector A in this case is actually equal to 0 degree, meaning that the flux produced in this situation is a maximum. But from the figure 5.2, okay, since the plane of the area is parallel to the magnetic field, okay, so that the vector of area perpendicular to the surface of the area, so the angle here is 90 degree. Okay, based on the formula of magnetic flux, BA cos theta, so when the angle is 90 degree, so the flux in this case is actually equal to 0. So as a note, you have to remember that vector A, the direction of vector A always perpendicular or normal to the surface of area A. And the magnetic flux is proportional to the number of field line passing through the area. Example 5.2. we have a single turn of a circular coil with diameter 3 cm is placed in the uniform magnetic field. The plane of the coil makes an angle 30 degrees to the direction of the magnetic field. If the magnetic flux through the area of the coil is 1.20 milliweber, calculate the magnitude of the magnetic field. First, we have to illustrate the position of the plane which is respective to the direction of magnetic field. First, we have to sketch the direction of magnetic field, B, and then from the statement given, the plane of the coil is 30 degrees to the magnetic field. So this is the plane of the coil, okay, and the plane is actually 30 degrees to the direction of B. And for this situation, we have to remember that the direction of vector A is always perpendicular to the surface of the coil or normal to the plane. So from this figure, you should know that the theta for application of magnetic flux, okay, is actually 60 degree. Okay, next we have to calculate the area of the coil, and for a circular coil, the area should be pi d square over 4. And the diameter is given 3 power of negative 2. Okay. So, the answer for the area is actually 7.07 power of negative 4 meter square. From the formula of magnetic flux, which is BA cos theta, and the flux is already given, which is 1.20 milli. Okay, so B, an area which is calculated, is 7.07 power of negative 4. And we know that the theta in this case is actually 60 degree. So, the B or magnetic field for this situation is actually 3.40 Tesla. Induced EMF. Faraday's law of electromagnetic induction. Faraday's law is the law that we use to calculate the magnitude of induced EMF. That's why Faraday's law states that the magnitude of the induced EMF is proportional to the rate of change of magnetic flux. Mathematically, induced EMF equal to the negative change of magnetic flux to the change of time. And the negative sign in this formula indicate that the direction of induced EMF always oppose the change of magnetic flux producing it. And this is actually referred to the Lenz law. The Lenz law is used to determine the direction of induced EMF, and the Faraday's law is to calculate the magnitude of the induced EMF. For a coil which is connected in series to a resistor of resistance R, the induced EMF will generate through the coil and will also induce a current through the coil. The induced current is given by the induced EMF, which is equal to the negative N change of magnetic flux to the change of time, and we know that induced EMF is actually equal to the IR. When we arrange the equation, induced EMF equal to IR, and this is the Faraday's law, and change of magnetic flux to the change of time. To calculate the magnitude of induced EMF, the negative sign can be ignored. And for a coil of N turn, each turn will has a magnetic flux of BA cos theta. Therefore, the magnetic flux linkage or the total combination amount of magnetic flux for all the turn, we can calculate by using the magnetic flux linkage equal to the N number of turn time with the magnetic flux for each turn. Example 5.4. The magnetic flux passing through a single turn of a coil is increased quickly but steadily at a rate of 5.0 power of negative 2 Weber per second. If the coil have 500 turns, calculate the magnitude of the induced EMF in the coil. For the solution, first we have to list down all the information given. So we know that the number of turns is 500 turns. And 5.0 power of negative 2 Weber per second is actually change of magnetic flux, rate of change of magnetic flux, but this is for a single turn. So to calculate the total induced EMF, okay, by you refer to the Faraday's law, induced EMF, okay, since we have number of turn is 500, so N time with the rate of change of magnetic flux, okay, and the number of turn is 500, change of magnetic flux per change of time is given 5 power of negative 2. So from the substitution value and the calculation, we got the induced EMF for the total number of turn is actually 25 volt. Example 5.5. A coil having an area of 8 cm square and 50 turns lies perpendicular to a magnetic field of 0.20 Tesla. If the magnetic flux density is steadily reduced to 0, taking 0.50 second, determine the initial magnetic flux linkage and the induced EMF. First, let's sketch the problem given. Firstly, choose a direction of magnetic flux density. For example, pointed to the right on x-axis. And we have a coil which is perpendicular to the magnetic field. From this figure, since the vector of area is perpendicular to the surface, hence, the angle theta between the vector of area and the magnetic field is 0. So, to calculate the initial magnetic flux linkage, okay, initial flux, we know that equal to the number of turn time with the flux for single turn. Okay, so we have N, and flux is actually B A cos theta. And for the flux initial, okay, the B is supposed to be initial magnetic field. Okay, by substitute the value, number of turn is 50 turns, and we have the initial magnetic field 0.20, and the area is 8 power of negative 4, and the theta is 0 degree. Therefore, the initial of magnetic flux linkage equal to 8.0 power of negative 3 Weber. Question B. We have to calculate the induced EMF in the coil. First, we have to consider the factor that changes in this question, or the quantity that change in this question. So, the question already state that the magnetic field is reduced from 0.20 Tesla to 0. So, we know that the change is based of magnetic field. So, we can rewrite the equation of induced EMF, okay, and the factor that constant in this situation, which is number of turn, cross-sectional area, and the angle of vector A and the direction of B. Okay, and the changes is due to the magnetic field. So we know that change of magnetic field is the final magnetic field minus with the initial magnetic field. And by substitute the value, number of turns is 50 turns. Okay, cross-sectional area 8 power of negative 4. And the theta for this case is 0 degree. And the B final is 0. The initial of B is 0.20. And the time taken to reduce 2 to 0 Tesla is taken for 0.5 seconds. So the induced EMF is actually 1.6 power of negative 2 volt.